So now that we've shown three, arguably four, different ways of doing this stuff, let's take a look and see what the pros and cons of each approach will be. And not surprisingly, they're trade-offs. First, just from a programming point of view, the iterative approach, the apply all iter solution, which, as you can see here, just goes through in one thread, forks all these tasks. They get put in the deck of that thread, get stolen by other threads in the worker pool, thread pool, and then we come here and we join, all in the same thread. That's pretty darn simple to program, pretty darn simple to understand, not unlike your programming assignment for assignment number 3. Oh, speaking of which, I'll have that out later today. 3B will be out shortly. However, if you take a look at the stats here, this is the running the program. It uses some of those helper methods on fork join pool to get some metadata about the runtime behavior of this particular, of these different implementations. You can see that apply all iter has a high steal count. And that's because it's putting everything in one thread, and then all the other threads in the pool have to steal from it. And as a consequence of this, it runs relatively slowly. So performance is slower. Of all the approaches, it's the slowest one because the overhead of stealing degrades scalability, let's put it that way. And actually, I need to rerun these experiments now because when I ran these things, this was on a quad-core machine. I now have a 6-core machine, and so I want to see if it works better with more cores. It probably will, but I'll be curious how it changes the behaviors. In contrast, the recursive decomposition approaches, the apply all split index and apply all split methods, do many fewer steals, about half as many steals. And as a consequence of that, the performance is better. And you can also see here that test apply all split index, that's the one that passes the indices in as opposed to doing the sublists. That one is a little bit faster than apply all split, which is a little faster than, they're both faster than apply all iter. So the point of this is arranging your code to partition things with recursive decomposition yields to less work stealing, yields to better performance. I mean, obviously, there's other factors at play, like memory copying and method calls and all this good stuff. So it's not totally for free. Recursion doesn't come for free, but it's not too much overhead, and you can see it performs better. But I think you'll also agree that this code here is a lot more complicated to look at and to write than that code here. This code is really simple because you're just whizzing down in one array call, forking galore, and then you're whizzing down in another for each call, joining. So much simpler to understand, much simpler to reason about, much simpler to program, whereas this code is like, oh my God, what's going on here? Although this is really not that hard, honestly. And once you understand the fork join pool, they always look sort of like this. You know, that's a very canonical way of doing things to split things up. And it also does some extra work with respect to those method calls and data copying and so on and so forth. Another thing to note, and this might be within the margin of noise, recursive actions overhead appears to be a little bit lower than recursive task. And that, again, is probably not so much because of the fact that recursive action is a faster implementation of recursive task. It's really because of the copying that's going on with recursive tasks with those sublists. Yes, William? Okay, so the question here is, when you have a fork join pool, and how does it decide which thread to run? So remember how the fork join pool works? There's a pool of worker threads, each of which has its own deck. And as long as there's any work in its deck, as long as there are tasks or subtasks in its own deck, a fork join thread, a worker thread, will always try to pop the top item off of its deck and then run it. So if there's work to do, it does it out of its deck. But when it doesn't have any work in its deck, when it's playing without a full deck, when it has nothing in the deck, it will turn around and go try to steal from somebody else's deck who might have something in it. And the way that the stealing works, as I mentioned before, is it's done randomly. So think about, like a random number generator. Let's assume, for sake of argument, you've got 4 threads in your fork join pool. And one thread discovers, aha, I don't have anything in my deck. And so in that particular case, it will consult a random number generator that will say, go look at someone else's deck, obviously not your own deck, look at somebody else's deck, try to randomly steal from the end of somebody else's deck. And if there is anything in that deck, it'll be stolen. If there's not anything in that deck, it'll randomly try someplace else. So it'll keep trying. So I think you're asking when you invoke, are you asking when a non-fork join client, so the question was, how do you start this whole thing in motion? So if you're a non-fork join client, so if you think back to the program, let's see, we'd have to go a bit back here, but if you're a non-fork join client, you're like the call to apply all iter, or apply all split, or apply all split index, whichever one of those things you're. Whoever calls that method, that's what invokes the original splitter task or the original thing to start things off. So in that case, that non-fork join client thread sticks the task into the shared queue, and then somebody in the worker thread pool, who knows, it doesn't matter, that could be random too, will wake up and say, aha, there's work for me to do, and I'll take it out of there. Yeah, so good question. Other questions about how this works? So recursive task may have this copying overhead that's a little bit higher. However, as we saw here, recursive action is a bit idiosyncratic. And that's because we had to figure out some way of being able to treat the list and convert it into an array, or something, an array of the appropriate size with the appropriate type, which for various reasons in Java is wacky and cumbersome. I wish there was a cleaner way to do this, but this is kind of the way to do it. Okay, so that is the end of fork join.